Alright, welcome back everybody. In this video we're going to discuss information from section 15 of Unit 1 of AP Calculus, connecting limits at infinity and horizontal asymptotes. This first video is going to focus on actually calculating limits as x approaches infinity or negative infinity. And then in the next video we'll start to apply that concept, but this first video is going to focus on how we're going to calculate these limits as x approaches infinity or negative infinity. Okay, so you see a little bit of narrative here, and notation. This is how we write the limit as x approaches infinity and the limit as x approaches negative infinity. That shouldn't come as a surprise to you, based off of things that we've seen thus far. And in all honesty, since I've been teaching AP Calculus, the vast majority of the time when I find the limit as x goes to infinity or the limit as x goes to negative infinity, I'm typically doing that numerically using a table of values generated on my calculator, and it's going to be a little different from how we were finding limits at finite values. There's an easier way to do it than if we tried to do it using those same old techniques that we had. Or, we might do it algebraically. I'm going to show you algebraically how to handle rational functions, or one way you can handle finding limits as x goes to infinity or negative infinity of rational functions algebraically. A lot of times if we do it algebraically, we end up just kind of thinking, what happens if x gets really, really big? Or x gets really, really big, only in a negative direction. I want to make an Ed Sullivan reference here, but I feel like that would go over the head of the vast majority of my audience, since Ed Sullivan was long gone even before I was born. Alright, anyway, sorry, I digress. Alright, so first off, how do we find them numerically? So we're going to make a table of values on our graphing calculator, just like we did before. The one big difference is when you go to your table set screen, you should have an option for your independent variable. You want to change that over from auto to ask. And that's what it looks like, or should look like, on the TI-83 or 84 models. On my 89, it looks a little different in my table set screen, but not a lot. I can go down here to my independent variable and go ahead and change that to ask. Okay. And now that I have that, when I go to my table screen, what I can do, instead of it giving me the x values, I still have some residual x values here, but I can type over them. So if I want to find, the value of the function at 10 and 100 and 1,000, I can just go through and type those values in as my independent variable. This comes in really handy when we're finding the limit as x goes to infinity, because, if I set up my table to count by some increment, it would take much longer than what I will do by just typing in those x values. And usually my recommendation for people is, if you're finding a limit as x goes to infinity, that you start by putting 10 and then going up by powers of 10, just like I did here, 10, 100, 1,000, 10,000, etc. And if you're going to negative infinity, start at negative 10 and go by multiples of 10, negative 10, negative 100, negative 1,000, counting down that way in your table. And if you do that, you should see in your y column here that you're going to approach some limit. So whatever function I have typed into my y equals screen, I think it's left over from the last lesson, it looks like that function as x goes to infinity, the y value it looks like is approaching 2. So let's go ahead and we'll work through a couple of examples doing this on our calculator. First, we're going to find the limit as x goes to infinity of 2x cubed minus 5x plus 6 all over 4x cubed minus 7. So I'm going to go ahead and start with 10, 100, 1,000, and you'll also find that some functions, this one won't be one of them, but you'll find that some functions grow so fast that you actually need to count a little slower for your x values because they get remarkably big way too fast than we can work with. Alright, so let's go ahead and type our function into the y equals screen. Y equals 2x cubed minus 5x plus 6. All that over 4x cubed minus 7. So we've got our function typed in. Now I think my table's going to keep those values that I already typed in just a moment ago. So we'll see, hey, it did. And we see what's going on in the right-hand column here. We've got 0.48986. And then we've got 0.49988. And it looks like all the rest of them round to 0.50000. If I round them to 5 decimal places. And so we're going to say here that the limit as x approaches infinity of 2x cubed minus 5x plus 6 over 4x cubed minus 7, that's going to be 1/2, or 0.5. Okay, and a lot of times when we're finding these limits as x goes to infinity on our table numerically, or on our calculator using the table numerically, it's pretty obvious what value we're approaching as x approaches infinity. Okay, let's go over to the next page, and we'll look at example 2. In this case, we're going to negative infinity, so I'm going to start my table at -10 and type those values in. And we'll see what happens. All right, so let's first type our function in. 3x squared minus 5x plus 3 over square root of 4x to the 4th minus 2. And my table's already set up to ask, and now I just need to type values in: -10, -100, -1000. Oops. By the way, the other thing is this overwrites, so I've got to remember to keep moving down a block as I'm entering these bigger and bigger values in here. All right, and so we see 1.76504 and 1.52515 and 1.50250 and 1.50025 and 1.50003. And so it looks like the limit as x goes to negative infinity of this function is approaching 1.5. Okay, now say you did this problem and you didn't get those values on your table as you're working along. Chances are that you've probably typed your function in wrong, more likely. Okay, so how do we find the limit as x, next question, how do we find the limit as x goes to infinity and x goes to negative infinity of f of x algebraically? And I said a lot of times you're just going to consider what happens when x gets really, really big or really, really big in a negative direction. But a very common limit that we find algebraically as x goes to infinity are rational functions. Those are very interesting functions for us when we're looking at limits approaching infinity. And so the way I tell people to do this is a little bit different from how some people tell you to do it, but it works just the same. So what I'm going to do, find the largest power of x that appears and divide all the terms by that power of x. Okay, so then what we'll do once we've done that is we will consider what happens to all the terms as x gets really, really big. And then there's some things to look out for here. What we've got here is kind of a special case scenario, if the largest power of x that appears is in both the numerator and denominator, we're going to have a finite limit. If the largest power is only in the numerator, the limit's going to approach infinity. If the largest power is only in the denominator, the limit will approach 0. I can actually use that to keep myself from having to do any work. I can kind of just look at the limits and see when it's either of these last two situations. If the largest power of x appears only in the numerator, that limit's going to approach infinity. If the largest power appears only in the denominator, that limit's going to approach 0. So let's take a look at what this looks like. In this case, example 3, the largest power appears in both the numerator and the denominator, which means we're going to have a finite limit. I'm going to divide everything by that largest power of x, which is x cubed. And what happens when I do that? I divide this by x cubed, and this by x cubed, and this by x cubed, and this by x cubed. That takes care of my numerator. And then I do the same thing with the terms in the denominator. I divide all of them by x cubed. And now I think, what happens as x gets really, really big? Well, these two terms don't change because they're just constants. All the rest of the terms, as x gets really, really big, all of these terms approach 0. 4 divided by a number that's getting infinitely large approaches 0. 5 divided by a number that's getting infinitely large squared approaches 0. And so all of these terms that are highlighted in green here approach 0, and our limit just ends up being 7/4. All right. Let's look at example 4. You can use what I said at the end of this. If you look at this, you notice that the largest power of x that appears is only in the denominator. So that tells us that this limit is going to approach 0. Okay. If you wanted to go through the algebraic technique, you can see why this becomes 0. Namely, if I divide everything by the largest power that appears in the fraction, that's dividing everything by x cubed. So all of these things that I'm highlighting in green, those all go to 0. And really what we end up here with then is we end up with 0/7, and 0/7 is 0. Okay, that's where we're going to call it quits for this video. You now have seen ways to find limits approaching infinity numerically using a table of values on your calculator, and you've also seen how to find limits algebraically, specifically of rational functions. And we'll pick back up next time with some applications of these limits approaching infinity. Okay, see you then. Have a great rest of your day.